Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. Today, we are going to have our second lecture on the multi-head attention. If you remember, in the previous lecture, we went through the conceptual overview of multi-head attention and how the mechanism actually works, how we split the query key and value vectors into multiple different heads, and how each of the heads eventually leads to a different attention score. And that actually helps us in capturing two different perspectives. With just the self attention mechanism, we can capture only one perspective of a given sentence or a given paragraph. But in some cases, we would like to essentially compute the concepts in a lot more detail or from a lot more perspectives, which is not possible through just a self attention mechanism. And that's why we have the multi head attention mechanism, where each head allows us to compute a different perspective. So we saw the whole process in the previous lecture. Today, what we are going to do is that today we are going to take a matrix. We are going to take an actual input embedding matrix, and we are going to see step by step about how the multi-head attention works in practice. So this is going to be a mathematics based lecture. The previous lecture was more about intuition, but here we are going to go step by step with respect to mathematics, and parallelly I'm also going to show you the code for how the multi-head attention function is written. And by the way, what we are going to cover in today's class is exactly how the first multi-head attention implementation works in practice. So, whatever we have done until now in this lecture series, starting from self attention to causal attention to the first lecture of multi head attention, it all comes to a culmination point in this lecture where we'll code out the entire multi attention class in multi head attention class in Python. And I'll also show you the step by step mathematical derivation and every matrix multiplication in a lot of detail. First, let's do a quick overview of what we learned in the previous lecture. In the previous lecture, we saw that if you have sentences such as this, the artist painted the portrait of a woman with a brush, this can be viewed in terms of two perspectives. Either the artist painted the portrait of a woman using a brush, or the artist painted the portrait of a woman with a brush. So the woman had a brush in her hand. It can be two different perspectives, right? But a self attention mechanism can only capture one such perspective because there is only one attention scores matrix. Either we can have this or we can have this. So then the question is, can we somehow extend the self attention mechanism so that it can capture multiple perspectives? So what we did was a single head can get us one attention score. So what if we have multiple heads, right? So what if we have two self attention mechanisms instead of one? And then we saw how to implement this multi-head attention step by step. We started with an input embedding matrix. The artist painted the portrait of a woman with a brush. We saw that the first step which is done is that we decide the output dimension. And this is going to stay the same in today's lecture as well. We have to decide the output dimension and we have to decide the number of heads which we want, the number of attention heads. So in our case, in the previous lecture, we had output dimension equal to 4 and number of attention heads equal to 2. So the head dimension is the output dimension divided by the number of attention heads, that's equal to 2. This is the dimension of each head. So what actually happens when we start doing the calculation is that we split the trainable query matrix, the key matrix and value matrix into two parts, and that eventually splits the query vectors, the key vectors and the value vectors into two parts. Why do we have two parts? Because there are two attention heads. So there is one copy of q, k and v, which is the query key and value matrix for each head. And now that we have two copies of the query key and value, it essentially leads to two attention scores. So this is the attention scores matrix calculated from the first head, and this is the attention score matrix calculated from the second head. This right here is the most important point in the multi-head attention mechanism workflow, because each attention scores matrix here essentially represents a different perspective. This was not possible with just the self-attention mechanism. Now we have two attention scores matrices, right? So each can capture a different perspective, and that's the main advantage of multi-head attention. Then what we do is, after we have the attention scores, we do the scaling with square root of the keys dimension. We apply softmax, causal attention, and if we want, we can do dropout also. That leads to the attention weights, the head 1 attention weights and the head 2 attention weights. And then what we do is that we multiply the attention weights of the head 1 and head 2 with their corresponding value vectors, and then we get the context matrix for head 1 and head 2. We merge these context matrices and then we get the final context matrix, which now is a mixture of two perspectives. So remember, the more the attention heads we have, the more the perspectives we can capture into our final context matrix. That's exactly how the multi-head attention actually works in practice. We also saw a cool visualization towards the end where we took a pre-trained large language model and we all actually explored inside the attention heads. So today, as I mentioned, we are going to do a mathematical calculation of exactly how the multi-head attention works. So I'm going to show you every single matrix multiplication from scratch, and then I'm also going to show you how it relates to the code for the multi-head attention. So here, if you see, this is the multi-head attention class, and if you just see the class without understanding the mathematical details, this all might seem a bit confusing to you. But I will take you today through the entire mathematical derivation, and then I'll show you that it's actually directly mapped to the code. And then understanding the code becomes that much easier. So let's get started. Today, the example which we are going to consider is this example where we'll start with an input embedding matrix. Okay. So the input embedding matrix is X and there are three tokens essentially. Let me change my color here so that maybe I'll change it to this new color over here, which is orange. So this is my input embedding matrix here. The way to visualize this matrix is that there are three tokens. This is token 1 that corresponds to the first row. This is token 2 which corresponds to the second row. And this is token 3 which corresponds to the third row. And every token essentially has a certain dimension. That's my input dimension. And this is going to be equal to 6 in this case. So there are three tokens and each token has 6 dimensions. But as you see, this is a tensor with three dimensions over here. So what's these three? The second is essentially just the number of tokens. The third is essentially the input dimension d in, So this is the tokens, this is the D in. But what's the first dimension? The first dimension is essentially the batch size. So we are going to just pass in one batch for the sake of simplicity. But if there are two batches which are passed, then this will be of a size 2 by 3 by 6. If there are three batches which are passed together, then this will be of a size 3 by 3 by 6, etc. Right? But for the sake of simplicity, I am going to assume that just one batch is passed at one time. But remember that whenever you write the code for the multi-head attention block, it always starts with the input embedding matrix with three dimensions. So when you go to the code, you'll see that we start the forward method of the multi-head attention class with three dimensions: the batch size, the number of tokens, and the input embedding dimension. That's the x dot shape, right? So this is my input embedding. So just to give you a quick recap of what this is if you remember the journey of the token through the, so we had a lecture regarding the journey of a token through the LLM architecture, right? There is a whole data pre-processing step where every token essentially gets converted into something which is called as the input embedding, which is the summation of token embedding plus position embedding. And we call the input embeddings as uniform. Essentially every token gets its own uniform. So the input embedding for every token which I'm showing over here is actually that uniform. So every token has its own row, right, which is a vector of 6 dimensions. That's its input embedding, which is the summation of token embedding plus position embedding. If you have not seen that lecture before, I highly recommend you to go through that lecture, which is titled Journey of a Token Through the LLM Architecture. So now we have done the first step, which is essentially defining our input, which consists of 3 dimensions. All right. Now next, let's go ahead. To apply the multi-head attention mechanism, as we saw in the previous lecture, we have to decide two things. We have to decide the output dimension, and we also have to define the number of attention heads which we want. Why do we need to decide these 2 dimensions? Because it eventually decides the dimension of each attention head which I have, which is called as head dimension. Remember, the head dimension is going to be d out divided by n heads. So in this case, what I'm going to do is that I'm going to decide my output dimension equal to 6, and I'm going to decide the number of heads to be equal to 2. So you can do a calculation of what each head dimension will be. It's going to be 6 divided by 2. So each attention head is going to have 3 dimensions now. Okay, great. The next step which I'm going to do is I'm going to multiply my input embedding matrix with my trainable query key and the value matrix. So first I have to initialize these matrices, right? I have to initialize. So remember my x now, which is this input, has is 1 by 3 comma 6. So if you forget this first batch, for now it's 3 by 6. So if you want to multiply it with trainable query matrix, trainable key matrix, and trainable value matrix, the first, the dimensions of this, the dimensions of this are d in comma d out. The dimensions of these trainable matrices are always d in comma d out. And remember, now we have finalized d in and d out. My d in is equal to, my dimension in is equal to 6, and my d out is also equal to 6. So my trainable weight matrices for the query key and value will all be 6 by 6 matrices which are initialized randomly. So that's what I'm going to do over here. I'm initializing the trainable weight matrices for the key, query, and value, and these will be 6 by 6 matrices. So this is for WQ, this is for WK, and this is WV. Remember, all the values inside these matrices are completely random right now. Our goal later through back propagation is to optimize these values so that the next token is predicted correctly. Once I have these trainable weight matrices, the next step what I'll do is that I'll take my input and I'll multiply with these matrices. So I'll multiply x with wk, x with wq, and x with wv. So remember, my x is now 1 by 3 comma 6. So if I multiply it with 6 by 6, that will lead to again a 1 by 3 comma 6 matrix. So after this multiplication, I get the keys matrix, which is 1 by 3 by 6. I get the queries matrix, which is 1 by 3 by 6. And I get the values matrix, which is 1 by 3 by 6. I want you to pay very close attention to these three values over here. Remember, we started out with an x input whose dimensions are batch size, number of tokens, and D in. Now check the dimensions of these queries, keys, and the values. The first is, of course, the batch size. The second is the number of tokens. So these two remain the same, but the third is now D out. So instead of the input dimension, we are now in the output dimension space. So the keys, queries, and values are all of the dimensions of batch size, comma number of tokens, comma output dimension. And until now, we have not applied the multi-head attention at all. But bear with me, we will apply it later. So let's go to the code right now. We have the x dot shape, which is b comma number of tokens comma the input dimension. And then what we are going to do is that in the init method, so if you see, we have to initialize the trainable query key and value matrices, right? That's essentially done over here. The query, the key, and the value matrices are initialized through a linear layer of a neural network, and the bias term is equal to 0. What this essentially means is that when you do self dot, or when you pass x, which is the input, through the trainable key weight matrix, it essentially takes a multiplication of the trainable key matrix multiplied by x. This is exactly what we wanted, right? To get the keys, queries, and the values, we just have to take the multiplication of the input embedding matrix and the trainable query key and the value matrices. That's what's done in this step. So here, although you cannot see a direct multiplication operation, here x is being passed, x, which is my input, is being passed as an input to this w key, which is the linear layer of a neural network. This essentially is a multiplication because the bias terms, if you see, the bias terms are set to 0. The reason we use nn.linear instead of nn.parameter is that nn.linear just has an optimized initialization scheme for the weights. So that helps in our back propagation later. But remember, in this part, what we are doing is that we are calculating the, so this is calculation of the keys matrix, which is represented by uh, this k over here, this keys matrix. This part is the calculation of the queries, which is the input multiplied by the trainable query matrix. And the third part over here, or the third line, is the calculation of the values matrix, which is the input multiplied by the trainable value matrix. So until this point in the code, we have obtained the keys, queries, and the values. And remember, its dimensions are batch size, number of tokens, and the output dimension. Now the real magic of multi-head attention starts after this point. Remember what we saw in the previous lecture. What we saw in the previous lecture is that once we have the query key and the value matrices, depending on the number of heads, these matrices are split into parts, right? So here, if you see, this whole this whole trainable this whole trainable query matrix which was there, it was essentially split into two parts because there are two heads. This is exactly what we are going to do in the code right now, or this is exactly what we are going to do in the mathematical calculation right now. If you see closely, the last dimension is d out, right? What we are going to do is that we are going to unroll this last dimension into two parts. So currently the dimensions of this keys, queries, and the values, they are b, batch size, number of tokens, and the output dimension, right? We are going to unroll the output dimension into two parts. What this means is that instead of having a 1 by 3 comma 6, we are going to unroll it to number of heads comma head dimension. Now check this out carefully. We have defined d out, which is equal to 6, and we have defined d number of heads, which is equal to 2, right? That means that the head dimension is equal to 3. Essentially what this means is that each head has a dimension of 3. So if you have this query matrix now, which is a 6 by 6, so 1 2 3 4 5 6, and if I'm going to repeat this 6 times, let's look at my query matrix right now, right? So actually my queries is 3 by 6, sorry, 1 by 3 by 6. So I just have to have 3 rows. So now this is my query, right? But now instead of having 6 columns, what I'm saying is that there are two attention heads. So each head should get a dimension of 3. So I should split it into two parts. This should be my head number 1, and this should be my head number 2. So this entire dimension of 3 by 6, right? So then essentially this will be 3 by 3, and then essentially this will be 3 by 3, or rather 1 by 3 by 3 and 1 by 3 by 3. So another way of saying this is that instead of having a 1 by 3 by 6, I will have a 4-dimensional tensor which is 1 by 3 by 2 by 3, where now d out is just replaced by number of heads and head dimension. And there is a very easy way to actually visualize this. If you can easily visualize this, right? Number of tokens comma d out, that's essentially just 3 rows and 6 columns, right? Number of tokens comma d out, which was this, is just 3 rows and 6 columns. But now 3 by 2 comma 3, you can visualize it like this. There are 3, so um, this is token 1, this is token 1, this is token 2, and this is token 3, right? And earlier, each token essentially had 6 columns associated with it. The first token had these 6 columns associated with it because the output dimension was 6. But now you see these 6 columns have been unrolled into a three column and 3 column. So essentially what is done is that after you divide it into two parts, um, this thing is essentially brought over here. This thing is essentially brought over here, and this is essentially brought over here. So now what I have is that 1, 2, 3, and let me write it by brown. 1, 2, 3. Then 1, 2, 3, and let me show this also by brown. 1, 2, 3. And last I have 1, 2, 3, and brown again. 1, 2, 3. So what is done is that my token 1, this is now my token 1, this is now my token 2, and this is now my token number 3. And token 1, instead of token 1 having all these 6 values together in a row, the first row now corresponds to my head 1, which are these 3 values over here, and the second row now corresponds to head number 2, which are these 3 values over here. Similarly, for token 2, this is my head 1 and this is my head 2. Similarly, for token number 3, this is my head 1 and this is my head number 2. So this is what it means when we say convert a 1 by 3 comma 6 or 3 by 6 to 3 by 2 comma 3. So now this is a 3 by 2 comma 3. So this is exactly what I have written over here. A 1 by 3 comma 2 comma 3 looks like this. There are 3. Why is it 3 comma 2 comma 3? Because there are 3 tokens. 3 tokens. Each token has 2 rows and 3 columns. So token number 1 has each token has 2 rows and 3 columns. So token number 1 has 2 rows and 3 columns. Token number 2 has 2 rows and 3 columns. Token number 3 has 2 rows and 3 columns. This is exactly what can be seen over here. Token number 1 has 2 rows and 3 columns. Token number 2 has 2 rows and 3 columns. Token number 3 has 2 rows and 3 columns. And what does each row in each token correspond to? The first row corresponds to head number 1 and the second row corresponds to head number 2. So now imagine that one token, right? We are looking at the queries. So the first token had some sort of a input embedding that is split into two parts. Half of it goes to head number 1, which is the first row, and half of it goes to head number 2, which is the second row. And that's done in a similar way for token number 2 and token number 3. So this is the reshaped queries matrix. So essentially reshaping just means splitting it into two. So visually splitting a matrix into two looks easier, right? But when in the code you see these unrolling parts, when you see these unrolling parts, it just gets very difficult to visualize. But here I am deliberately showing this visualization to you so that it's actually very easy. What does it mean to unroll the last dimension? To unroll the last dimension just means that you have this full dimension, which is 6-dimensional token. You split it into two and bring the second half below the first part. So that leads to a 1 by 3 by 1 comma 3 comma 2 comma 3 reshaped queries matrix, a 1 comma 3 comma 2 comma 3 reshaped keys matrix, and a 1 by 3 1 comma 3 comma 2 comma 3 reshaped values matrix. So this is done in the code also. In the code, what we have written here is that unroll the last dimension. So earlier we had b comma number of tokens comma d out, and now this is changed to b comma number of tokens comma number of heads comma head dimension. Number of heads is equal to 2 and head dimensions is 3. So that's 1 comma 3 comma 2 comma 3. That's exactly what's written here. We are going to unroll this to b comma number of tokens comma number of heads comma head dimension. And the way this is done is that the keys matrix which was originally there, right? We do keys dot view b comma number of tokens comma number of heads comma head dimension. Similarly for values, we do values dot view b comma number of tokens comma number of heads comma head dimension. Similarly for the queries, we do queries dot view b comma number of tokens comma number of heads comma head dimension. So these are the keys, values, and queries which are reshaped. So until now we are at this part where we have reshaped the keys, queries, and values to take into account multiple attention heads. Then what we are going to do is that so the keys, queries, and the values have been obtained. Then what we are going to do, we are going to group the matrices by the number of heads. So you see the problem here is that we have grouped by the number of tokens, right? We see the token 1, and within the token 1 there is the head 1 and head 2. But now what we have to do is that we have to group it by the heads. So instead of 1 comma 3 comma 2 comma 3, I want 1 comma 2 comma 3 comma 3, which means I want to interchange this and this. So essentially I want the dimensions of my matrices to be b comma number of heads comma number of tokens comma head dimension. So what this will do is that you see the queries matrix, initially we grouped it with token 1, token 2, token 3. But now we'll group it with head. So now this is my head 1 and this is my head 2. Then what will happen is that within each head there is this token 1, token 2, and token 3. And each token now has head dimensions which is equal to 3. So this is 3 dimension. Similarly, if you look at head number 2, the first row of head number 2 corresponds to token 1, token 2, and token 3. So you see the difference between this 1 comma 3 comma 2 comma 3. Here the grouping was with number of tokens, but now we have grouped it with head 1 and head 2. Why do we do this? Because it's just then easier to multiply, right? If you see, if you see over here, the advantage of these heads is that the queries, the keys, and the values have been split into multiple heads. So we should clearly see the different copies, right? Now that we have done this type of a grouping, we can clearly see the copies. This is the first copy, which is the queries. This is Q1. This is Q1, which is the queries for the first head. This is Q2, which is the queries matrix for the second head. So the division just becomes very easy. Whereas if you group it with the number of tokens, my head 1 is here, my head 1 is here, and my head 1 is here. So part of my head 1 is in this first row, part is here, and part is here. So it needs to be grouped together in one single place. So that's why we group it with the number of heads, because later remember that we have to then take the dot product between. So let's say this is my q1 now, this is my q2 now, this is my k1, and this is the k2. We have to take a dot product between q1 and k1 transpose, and we have to take a dot product between q2 and k2 transpose. Remember, this is exactly what we had done over here. We had taken a dot product between q1 and k1 transpose, and we had taken a dot product between q2 and k2 transpose. To take this dot product, all the to take this dot product, essentially head 1 needs to be in one place, q1 needs to be in one place, q2 needs to be in one place, k1 needs to be in one place, k2 needs to be one place. So that's why it's very important for us to group the matrices by the number of heads instead of grouping by the number of tokens. And this is what is done in the next part of the code. The next part of the code, we just take the transpose of these dimensions number 1 and dimensions number 2. So keys dot transpose 1 comma 2 just means that since Python starts with 0 indexing, this is index 0, this is index 1, and this is index 2. So we are going to take the transpose of these indices. These are going to be interchanged to number of heads comma number of tokens. So now we are going to be grouping by the number of heads. So all the keys, queries, and the values matrices are now transposed. And we have 1 comma 2 here because 1 is the this index and 2 is this index. So these need to be interchanged now. That's what's done in this part of the code. Okay. So until now we have the Q1, Q2, we have the K1, K2, and we have the V1, V2. So if we were to map it out to the steps which we had seen in the previous lecture, we have reached this part of the code where we have Q1, Q2, K1, K2, and V1, V2. Now let's go to the next part um, where we actually compute the attention scores. To compute the attention scores, what we have to simply do is that we have to look at Q1 and K1 and take their transpose. We have to look at Q2 and K2, take their transpose. That's it. So that's exactly what we are doing here. We are going to take the queries and we are going to multiply it with keys dot transpose 2 comma 3. Why 2 comma 3? Because now we are grouping by the number of heads, right? So when we look at one head, we essentially, so first what we do is that we look at the first head. So we have to multiply this with the transpose of this matrix. So what does it mean taking the transpose of this matrix? So it means that, so now the rows here are T1, T2 and T3, right? And the columns are the dimensions. So the rows here are the number of tokens and the columns are head dimensions, which means we have to take the transpose of these two. So multiplying Q1 and K1 transpose essentially just means taking the transpose of these last two dimensions over here for K1. Why the last two? Because we are already, so each row here corresponds to first token, second token, third token, and each column corresponds to the dimension, which are essentially corresponding to the last two dimensions. So multiplying Q1 with K1 transpose essentially just means queries multiplies by keys dot transpose 2 comma 3. So now we have this entire queries matrix, right? When we take this queries matrix and when we multiply it with keys dot transpose 2 comma 3, what will essentially happen is that first Q1 will be multiplied with K1 transpose and then Q2 will be multiplied with K2 transpose. So that's essentially what we are going to get over here. So if you think about the dimensions of the resultant matrix, what we are now doing is that we have this matrix queries, which is b comma number of heads comma number of tokens comma head dimension, and we are multiplying it with keys dot transpose 2 comma 3, which means these two are interchanged. So we are multiplying this matrix with b comma number of heads comma head dim comma number of tokens, right? So what will the multiplication result in? It's the number of tokens comma head dim multiplied by the head dim comma number of tokens. So it's going to be b comma number of heads comma number of tokens comma number of tokens, and that's just going to be 3 by 3. So if you take this multiplication, you will get this matrix which is of the size 1 comma 2 comma 3 comma 3. But now what this means is that this is head 1. This is actually head 1 attention scores. This is actually head 1 attention scores, and this is actually head 2 attention scores. And since these are attention scores, of course their dimensions have to be number of tokens multiplied by the number of tokens. So this is how we get the two attention scores in matrix multiplication, which is exactly what was done in the code also. Once we have which was exactly what was done in our visual lecture. Once we have Q1 and K1, we take this dot product. Once we have Q2 and K2, we take this dot product. So Q1 multiplied by K1 transpose gives us the head 1 attention scores. Q2 multiplied by K2 transpose gives us this head 2 attention scores. But I want you to pay very careful attention to the dimensions over here, because the dimensions are where people usually get confused, right? So you have this head 1, head 2, head 1, head 2, head 1 and head 2. So you have Q1, Q2, K1, K2, V1, V2. Then what you have to do is that you have to multiply Q1 with K1 transpose, Q2 with K2 transpose. And when you do that, you finally get this attention scores matrix whose dimensions now are B, which is the batch size, number of heads, because you have grouped by the number of heads. This is head 1 and this head 2. And why is this 3 comma 3? Because since it's attention scores, it has to be number of tokens multiplied by number of tokens, because the attention scores are calculated among every token. So this is now the two attention scores matrix which we have for the two heads. And this is exactly what is done in the code also. To get the attention scores, we have to multiply the queries and keys dot transpose 2 comma 3. This 2 comma 3 is very important because it's the last two dimensions which get transposed and which get multiplied. So the ultimate dimensions of the attention scores after we take the dot product for each head is b comma number of heads comma number of tokens comma number of tokens. This step is also called taking the dot product for each head. Why? Because first we multiply q1 with k1 transpose, that's taking the dot product for head number 1, and then we multiply q2 with k2 transpose, that's essentially taking the dot product for head number 2. Okay, so until now we have found the attention scores matrix. Now what we have to do is that we have to find the attention weights. So this is to get this, what we had seen in yesterday's lecture was to get the attention weights we have to basically first scale it, then apply softmax, then do causal attention, and if needed we can do dropout. So now this is exactly what is done in the mathematical calculations also. So let me take you through that. Okay, so we have the attention scores matrices now. What we'll first do is that we'll first mask the attention scores to implement causal attention. So to do this, so this is the head 1 attention scores and these are the head 2 attention scores. What we do is that the elements above the diagonal are replaced with minus infinity. We saw this in the causal attention lecture also. And the elements above the diagonal in head number 2 are also replaced with minus infinity. And what we'll do is that we'll also divide by the square root of head dimension. Remember, in self attention we divided by the square root of keys dimension, but now the keys dimension is equal to the head dimension. Each key dimension is equal to the head dimension, which is d out divided by number of heads, which is 6 divided by 2. So we'll scale it by the square root of 3. We'll scale it by the square root of 3 and then we'll apply softmax. What softmax will do is that it will make sure the elements with negative infinity are set to 0. Remember, in causal attention we cannot peek into the future. So for each token we only get the attention scores corresponding to that token and the tokens which come before it. And why do we divide by the square root of head dimension? This is just to make sure that the variance of the queries multiplied by the keys transpose does not blow up. Dividing by the square root of the head dimension makes sure that the variance of that dot product between queries and the keys transpose essentially stays essentially stays closer to 1, and that's important for us when we are going to do uh, back propagation, etc. We don't want values to be widely different from each other. So when we apply softmax we get the attention weights matrix, and remember that the dimensions of the attention weight matrix are exactly same as the dimensions of the attention scores matrix. It's going to be batch size, number of heads, number of tokens, and number of tokens. So the same thing here, batch size 1, number of heads. So this is head number 1, this is head number 2, and then 3 comma 3 because I have number of tokens equal to 3. These number of rows and number of columns also equal to the number of tokens. Number of tokens. But the difference now between the attention weights and the attention scores is that the attention score in the attention weights, if you see every row essentially sums up to 1. So we can also implement dropout after this, but I have not implemented it here for the sake of simplicity. So now what you can do is that you can go to the code and you'll see that the same thing has been implemented here. First, what we do is that we create a mask of negative infinity above the diagonal, which has been done over here. We create this mask of negative infinity above the diagonal. Then what we do is that we divide by the square root of the head dimension, and then we take the softmax. And if needed, we can also apply the dropout. So if you scroll up to the top, we can set the dropout rate. By default, I think the dropout rate we can set it to equal to 0 if we don't want any dropout. But if you randomly want to turn off certain attention weights, you can do that by applying a dropout rate of, let's say, 0.5. Okay. So this is how the until now we have calculated the attention weights and then applied dropout. Then what we do after we get the attention weights, remember the last step after getting the attention weights is that we have to multiply um, head 1, we have to multiply the head 1 attention weights with the value 1 v1, and we have to multiply the head 2 attention weights with v2. So let's see how that is done now in matrix multiplication. All right. So this is the attention weight matrix. So this is head number 1 and this is head number 2. And these are my values matrix, right? So my values is this is my v1, and this is my v1, and this is my v2. So h1 and h2. So what I'll do is that I'll simply multiply these two together. Now take a look at the dimensions of what exactly is being multiplied over here. So so b comma number of heads and b comma number of heads, that's the same for both these matrices or both these four dimensional matrices. They are both grouped by the number of heads. But what really we should check while multiplying is that this is number of tokens by number of tokens. So that's going to be 3 by 3. And this is number of tokens by the head dimension. So that's also 3 by 3. So when you multiply this, again the product is now taken into the number of tokens comma head dimension space. So we have 3 tokens here, and each head dimension is equal to 3, right? So when you multiply the attention weights with the values, you get the context vector matrices. So the first row over here is the context vector matrix for head 1, and the second is the context vector matrix for head number 2. And we have 3 tokens over here, so there are context vector for each tokens, and the size of each context vector is equal to the head dimension, which is equal to the number of which is equal to the last dimension over here, which is equal to the head dimension. Now if you scroll to the visual multi-head attention, this is exactly what we had obtained yesterday, right? We had obtained the head 1 context matrix and we had obtained the head 2 context matrix. Here also there were 11 tokens, and the size of each context vector was equal to 2, which was equal to the head dimension in this case. This is the same thing as what is being done over here. We have the context vectors for head 1 and we have the context vectors for head number 2, and when you go inside each head, the size is number of tokens, and each token has the context vector of size equal to head dimension. This is done in this part where we multiply the attention weights multiplied with the values. Okay, when we get the context vector. Now what we do is that when we get the context vector, remember that our final aim is not directly to get two different matrices, but we have to merge the context matrix for head 1 and the context matrix for head 2. We have to merge these context matrices, right? We don't have to keep them separate. So that part is still remaining, right? And to merge these, what we have to do is that we have to again group by the number of tokens. So that's why we need to reshape it again. Currently the dimension is b comma number of heads, right? It's grouped by the number of heads. So we need to reshape it again. You remember we did this step earlier once, where what we did is we actually uh, switched it. So we deliberately brought the number of heads before, so we want to group by the number of heads, but now we'll switch it back to the original configuration so that we group it by the number of tokens. So this is now token number 1, this is now token number 2, and this is now token number 3. The reason I want to group it by tokens is that eventually I want to merge the head 1 and the head 2 output for each token, right? So token 1, it has the head 1 context vector and it has a head 2 context vector. I don't want it to be separate, I want to merge. So then I'll merge these two together. Similarly for token 2, I have the head 1 context vector and I have the head 2 context vector. I don't want these vectors to be separate, so I'll merge these two. For token number 3, I have the head 1 context vector and I have the head 2 context vector. I don't want these to be separate, so I'll merge these two. And this merging is just easier if I group it by the number of tokens. So that's why we actually switch these positions once more, and that's the reason that there is one more transpose 1 comma 2 here. So once we get the context vector matrix, we'll again transpose 1 comma 2, so that we'll group again by the number of tokens. And once we group by the number of tokens, what we'll simply do is that we will merge. For the token 1, we'll merge the first row and the second row. So it leads to 6 values, which are the first two rows merged. Then for token 2, we'll merge these two. Head 1 context vector, head 2 context vector. that will give me these six values. And for token number 3, I'll merge these two vectors. So that will give me these six values again. So ultimately, the final resultant context vector matrix which I have will be batch size, number of tokens, and the output dimension. So you see what we did. Initially we started out with b comma number tokens comma d in, right? Then we went through a bunch of steps, and then ultimately we obtained the context vector which is b comma number of tokens, b comma number of tokens comma d out. This is the final context vector matrix, and this is again the last part of my code. The last part of my code is this context vector dot contiguous dot view. What this will do is that this will just merge the first row, second row of token 1, first row, second row token 2, first row, second row of token number 3, and it will give me an output context matrix of size 1 comma 3 comma 6. Remember, now the beauty of this vector matrix is that whenever someone looks at this size, they will just see 1 comma 3 comma 6. But the way we have reached this is that we actually obtained two context vectors, right? We obtained two context vector matrices, and then we merged them together into one. So this one final context vector matrix actually contains two perspectives. It contains perspectives from the head 1 as well as head 2. So it's much richer than having just the self attention mechanism producing a context vector matrix, because now we actually had multiple context vector matrices and we merged them together. If there were six attention heads, we would have six context vector matrices which would be merged together to give me my final context vector matrix. That's the beauty of multi-head attention. Although the dimension looks the same as it would have when we did self attention, but now the matrix is much more richer since it captures multiple perspectives. That's it. This is the last step of the multi-head attention, and I want to thank you all for sticking through this entire lecture and seeing all the steps. Especially when we look at matrices and dimensions, things can get a bit complicated. And when you look at this code directly, you'll think it's a bit complicated, right? But it's actually very simple. If you understand the mathematics with respect to matrices, then the code actually makes a lot of sense. This is the main class, the multi-head attention, which powers all the major large language models out there. Of course, there were a lot of improvements after this, such as KV caching, multi-head latent attention, flash attention, etc. But if you understand these three dimensions, b comma number of tokens comma d in, if you understand what this keys dot view, values dot view, queries dot view does, what transpose means, transpose 1 comma 2, how it relates to the handwritten exercise, you will find these things are not very difficult. So I highly encourage all of you to take a piece of paper and write all these things down as if you're following this lecture seriously. So once this class is actually defined, what you can simply do is that you can just take an inputs vector which is 1 2 3. So I have three rows over here, my three tokens, and each token is a six dimensional vector, the same example which we saw on the notes. And then we can just have, so here I'm having two batches though. I've stacked the inputs on top of the inputs. So remember, although in the handwritten notes we just took one batch, the code is powerful enough to change the first dimension to even two. So that's what I'm considering over here. I'm stacking these two inputs one on top of each other to create a batch, and then I just pass this entire input to this multi-head attention. That's it. And then I create the context vectors. So you'll see the first context vector is 1 by 3 comma 6. This is exactly the context vector shape which we had seen over here, um, 1 by 3 comma 6, and the second context vector is 1 by 3 comma 6. So this is the first batch, this whole thing is the first batch, and this whole thing is the second batch. That's why we have the size here 2 by 3 comma 6. If we had three batches, it would have been 3 comma 3 comma 6. So just within 5 to 6 lines of code, we have implemented the multi-head attention calculation. And here, if you scroll above, these are 20 to 25 lines of code, which is the mechanism which powers uh, or which is the brain behind why large language models work so well. These 25 lines of code actually encode the key advancement which happened in 2017 when the transformer block was introduced for the first time. And if someone just takes a look at this code, they'll find it difficult. But my main purpose of today's class was to link it to handwritten notes of mathematical derivation and also to an intuition which we looked at in the previous class. Only then I showed you the code so that you don't get scared or intimidated by the code. But if you're seriously interested about developing your understanding and never forgetting how multi-head attention works, take a piece of paper, write everything down so that you don't forget this at all. Now that we have completed this lecture, we have done multi-head attention, so we have finished these three parts. We are now fully ready to start learning about key value cache. Key value cache is that main mechanism which made multi-head attention much more efficient, and this serves as the bridge towards finally understanding multi-head latent attention. That is the real key innovation which was implemented in the DeepSeek paper. But to understand key value cache and to understand multi-head latent attention, it would have been very difficult for you to understand this if you did not understand today's lecture. So that's why we had all these lectures on self attention, causal attention, multi-head attention. So I want to congratulate you and thank you for reaching this part. Please stay with me. The later parts will be even more rewarding now that you have finished completing the lectures until here. So thanks a lot, everyone. Please make notes along with me so that you learn the most. Thanks, everyone. I look forward to seeing you in the next lecture.